How many of you were here last year and remember me speaking last year? Oh, some of you. Not enough though, so I'm going to have to repeat some stuff I said before. So really quickly, I borrowed this cable from the very nice guys at the back, and I just want to demonstrate something. This cable is about, how long would you reckon this cable is? Metre and a half? Metre and a half, right about a metre and a half. Does anybody know how long it takes for a signal to get from one end of this cable to the other? Metre and a half. Anyone want to guess? A couple of nanoseconds. Which is about right. In fact, it's probably around about... Electromagnetic radiation travels slightly slower in cables than it does through a vacuum. So light in a vacuum is about 300,000 kilometers a second. This is about 200,000 kilometers a second. It's about 66% or thereabouts, 2/3. So this is probably, I don't know, 7 nanoseconds thereabouts. So we need to keep 7 nanoseconds in mind, because that's the kind of distances we're going to be talking about. We're going to be talking about distances that are that long or shorter. So anytime you hear the word nanosecond, I want you to think about 30 centimeters. Or for you who are still operating in old money, just over a foot. Foot and a bit, okay? So around 30 centimeters. So anytime I mention a figure like that, the other thing I'd like to point out is that a millisecond is not a microsecond. You knew that anyway, but you'd be surprised how many people get confused by the sound. A millisecond is 1,000 times longer than a microsecond. And a microsecond is 1,000 times longer than a nanosecond, okay? And a nanosecond is how long? 30 centimeters. What do I point at, guys? Ah, there. That's the underarm one. So just a quick introduction to SNIA. SNIA is the Storage Networking Industry Association, 160 industry organizations that vary from networking companies all the way through to chip manufacturers to storage manufacturers. So there's a wide variety of people represented in SNIA in terms of the industry. We've got about 2,500 active contributing members in that group of industry contributors. And we've got about 50,000 end users and IT users that we talk to on a regular basis. And we run webcasts and et cetera, and it's independent, industry-neutral education that we're giving people. This is not about selling products, this is about selling concepts and technology. So SNIA is an industry body that represents the entire industry. And you can find us at snia.org. So, what we're going to cover today is persistent memory. I'm going to talk about a new technology that's just beginning to appear. And as a good friend of mine says, this kind of technology takes around about 2 Olympics. So we've done the 30 centimeter piece, okay, just to get you an idea of what a nanosecond is about. Now I want to explain how long it takes for new technology to go from, hey, this is really exciting, to everybody's using it and is bored by it, okay? And it's about 2 Olympics, or 8 to 10 years, roughly. So the stuff I'm talking about today will be so boring in 8 years' time, you'll all be going, meh. I've heard Alex's stuff before. We're using it regularly. But this stuff is relatively new, but it's very exciting, and it is incredibly important, because this is the biggest change we've had in the storage and memory industry in a generation. How long is a generation? I don't care. It's longer than, it's longer than it takes an electron to travel from one end of a cable to another, that's for sure. So we're going to talk a little about persistent memory, PMEM. I'm going to talk about what everyone should know about PMEM, what everyone forgets about PMEM, because it's a new technology. I'm going to talk about the hardware and how we address the hardware through programming. I'm going to talk about applications that can use this persistent memory. I'm going to talk about how to use this persistent memory going forward by changing applications, and what we've learned so far about the technology and where we're heading with it. And the first thing I want you to recognize is this phrase, persistent memory, PMEM, PM, call it what you like, but do not call it storage class memory. I will have to take you outside and beat you up, okay? We do not use the term storage class memory. Can you think, give me a good reason why you'd want to do that. Why would you want to talk about storage class memory? And the reason people talked about storage class memory originally was because this stuff is persistent like storage. Funnily enough, memory doesn't remember stuff in general. DRAM just, who calls it DRAM and who calls it DRAM? 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 Good Scots amongst us. So, in Scotland, everything's a DRAM. Cheers. The whole point about this being storage is that it's persistent. Its persistence is the important bit, and you'll see it's not like storage. This does not act the same way. You can treat it like storage, but that's a bad move because it's actually memory, and I'll explain the difference quite clearly between the two. So, what is persistent memory? You can do loads and stores on it. In other words, you can address it to the byte. And if you think about storage, the last thing you can do with storage is address it to the byte. You generally have to address it to the block. If you think about underlying disk technology, why do we have block devices? We have block devices because of disks. Why do we have disks? Because of IBM. When did we invent disks? About 1930 odd, so thereabouts, with drums, and then instead of spinning them that way, we decided to spin them that way and have the platters running flat, and we have arms, and blocks is a really natural way of dealing with the data on a disk. Really simple. But memory is completely different. It's byte addressable. We can go in there and we can individually address single bytes. So persistent memory, loads and stores like real DRAM or DRAM. But it's persistent like storage. And this causes all sorts of complexities. Now, you might think that having persistent memory is a blessing. Hurrah! Look, stuff I put into memory does not disappear. But that's actually a big problem, because how do you reset most servers these days? You power them off and power them back on again, and everything gets flushed, and you start from scratch because there's nothing in the memory. Imagine a server made up of persistent memory, and it's just run into a bug, and it's just overwritten an entire table in persistent memory. And you power it off, and you power it back on, and you've still got the same corrupt table in memory. Hey, it's difficult stuff. We need to deal with it slightly differently. What isn't persistent memory? Something that looks like an SSD. In fact, persistent memory is not made out of flash. It's made out of different technologies. Flash is not byte addressable. Flash is actually, we talk about pages of flash. A page is the individual addressable element in a flash chip. And those pages can be very, very large indeed. 128K is not uncommon for the addressing unit of flash. Okay, so this is not flash. This is byte addressable memory. So it's not persistent memory if it only speaks blocks. Or if it's too slow for loads and stores. Too slow, sorry. Monday morning. Or is it Tuesday morning? Who knows? You do. Too slow for loads and stores. And the reason we don't, that it needs to be, or is fast, is that if you think about doing a transition change, how many of you know about transitioning inside a chip in terms of moving from one task to another, doing a task switch or a context switch? Some people know how. How long does a context switch take? Depends. It does depend, but it's around about 500 nanoseconds. How many 30-centimeter chunks is that? 500. It's a lot. It's a huge amount of time. 500 nanoseconds is actually quite long. And if I can do a load or a store in less than 500 nanoseconds, then I don't really want to do a context switch. I just want to wait until the load and store is finished. Now, if I'm talking to DRAM, the kind of responsiveness, the latency in DRAM is around about 1 nanosecond or less. Persistent memory, the latency is around about 10 nanoseconds to 100 nanoseconds. So it's longer, but it's worth waiting for that load and store because the context switch is even longer still. And then we will look up to SSDs. What are we into with SSDs? Nanoseconds? No. Microseconds. So SSDs respond, or flash responds, in microseconds, which is quite a bit longer. Disks? Milliseconds. I mean, disks, 7, 8 milliseconds for a disk to respond. Long, long, long time. That's like from here to Paris and back. Though why anybody would want to go to Paris and back is beyond me. So, it's persistent memory if it's byte addressable. It's persistent like storage, but it's not persistent memory if it acts like a disk. In other words, you address it via blocks. Or something that's too slow for loads and stores. So there's a fundamental change taking place with this new technology, this new memory. By the way, I've mentioned the fact that it fits only loosely, but I'll mention it again. DRAM's really fast, but small and expensive. SSDs, flash, is big, capacious, but relatively slow, and this persistent memory technology fits in the middle. It's smaller than SSDs, but it's bigger than DRAM. It's faster than SSDs, but it's slower than DRAM. And it, in terms of pricing, sits around about in the middle as well. So it's 1,000 times faster than SSDs, but it's about 1,000 times slower than DRAM, approximately. These are all rules of thumb, okay? So we need a fundamental change to cope with this. So there's been an awful lot of work, and you'll see a number of technology companies and technologies, people working towards this, taking control of this new technology, managing it and delivering it out so that you can use it. And it's exciting stuff, very exciting stuff. I'll give you an example in a second. So there are two types of NVDIMM, non-volatile DIMMs, or persistent memory at the moment. The first one is N, which looks like DRAM, but is flash-backed. So anytime the power goes off, it simply dumps the contents of the DRAM that you're addressing to flash. You might think, that's a cheat, and you'd be absolutely right. It's a huge cheat, and it's also incredibly expensive, because not only do you have the cost of the DRAM, you've also got the cost of the flash. But it has its uses, and it was a good test bed for delivering this NVDIMM-P that we're beginning to see, which is persistent memory in its own right, that is it's not flash-backed, it's not DRAM, it's real persistent memory. And some of you may have heard of Intel's 3D Crosspoint. We're now seeing chips based on this out in the marketplace for DIMMs. But it does require a change to the hardware. I'll explain that in a second. And operating systems need to be able to take advantage of it. But I just want to point out the latencies in nanoseconds. So there you have the latencies of CPU to DRAM to NVDIMM to SSDs, all the way out to hard disks. And I just want to point out, these are factors of 10. That's a lot. So, hard disk is what? 10 to the 6 times slower than a CPU addressing a register. That's a big difference. Okay? So, what are the application areas for this new persistent memory? And funnily enough, it's not the classic storage ones. There are some new ones. I'll talk a little about things like Java support and Cassandra, et cetera, as an example. But databases where we're doing log acceleration or in-memory commit, really effective way of doing it. Storage for things like file systems, small file systems. There was a talk yesterday about Redis and Memcached. Those kind of things are ideally suited for persistent memory, because you don't need to flush them back out the disk. These, the structures can live on persistent memory and persist, which is part of the goal. Virtualization, big data, where you need fast IOPS. So I want to talk a little about the latency and performance of these devices. How many of you know what an IOP is? So an IOP is an I/O process. It's actually going out to a disk and reading or writing a block, remember it's block-based, of data. And doing IOPS is a relatively expensive thing. You're moving about 4K at a time currently with most IOPS. They're 4K in size, roughly. And we've been used to doing IOPS at the rate of around about 100,000 IOPS a second, perhaps up to 250,000 IOPS a second on very sophisticated and smart systems. With non-volatile, with persistent memory, we can build things that look like SSDs, but that run at 10 million IOPS. That's 10 million IOs a second. You ever heard a mouse squeak? It's about 20 kilohertz. This is 10 megahertz of IO. We can do huge amounts of IO against this stuff. It's incredibly fast, hugely faster than the fastest thing you've ever had go fast. Seriously, it's a ripper. So these kind of areas, application areas, are going to be increasingly important with non-volatile memory or persistent memory. But it's not, remember, storage class memory because it's byte addressable. Yeah? So the programming model we've got as well, we include storage APIs, and there's a reason for that. We've got 4 ways of addressing this stuff currently. And I'll cover some of them. So first of all, we've got a way of looking at it from a storage API way. We can look at this new persistent memory as just simply an I/O device, a disk. Okay? So we've got one where we can use persistent memory like an SSD, and we've got another one where we can go direct in. It's called DAX. And if you want to read up on this, if you just search on DAX, Linux and Windows use the same terminology, and unbelievably, they managed to agree on the terminology, direct access, DAX, and they both use it. Now, DAX allows you direct access to this persistent memory as a block device. But there's no paging, there's no caching going on. What's the other problem with a storage device? When I do an I/O, what do I have to do? I have to move the data. That's what an I/O is all about. Moving the data. Moving data is incredibly wasteful. Why would I want to go and move a 4K page to update a byte to then write out that same 4K page? Which is what a lot of the I/O that we do actually turns out to be, very minor, small changes. Or most of the I/O that we do is of the other form where we read the data and then we throw it away. We're not actually interested in it. We've read 4K, we're only interested in 4 bytes. And that's very common. And what DAX allows you to do is directly access this stuff as a 4K block, but we don't move it from anywhere to anywhere. It just happens to be there. That's its home, the bit where we address it, but we're addressing it as a block rather than as an individual set of bytes. And that allows our applications to move quite smoothly from using DRAM and I/O into using this persistent memory because we can make it look like a disk. We've also got this volatile capacity where we can actually go out and address it as basically RAM. For this, we need the support of new chips, and Intel and AMD are providing us with new chips. One of the problems we've got, let's say you put this new stuff in your server, you plug it in, and you start using it. Does the operating system understand the difference between DRAM and persistent memory? No. There's no way for it to differentiate. All this stuff is sitting on the memory bus. So what we're seeing is that Intel and AMD have invented a double anyone who knows anything about MMUs, they're called memory management units, to address both DRAM, the traditional stuff that we currently have, and also persistent memory, so that operating systems can differentiate between this super fast DRAM, but it's not persistent, and this fast stuff that is persistent. So we've got effectively a dual memory bus and dual memory spaces. We've got a memory space that addresses persistent memory and a memory space that addresses standard DRAM. So we actually need a change so that we can support this kind of addressing this stuff as memory, because the operating system needs half a chance to understand what it's talking at. So no application modification, use persistent memory as a fast SSD, super fast SSD. And then memory map pages into DRAM. We're still moving data about, though. Anytime you deal with something as an SSD, you're moving data from one place to another. DAX is direct access, which doesn't move the data, but is effectively addressing it in blocks. So it still looks like a storage device, but we're not actually moving the data. The data is exactly where it's supposed to be at the right time. And that's just basically big main memory. Is it useful? You bet. It's really useful because our applications don't need to change. And that's actually quite critical. So that was the way of doing DAX access as well. Then we've got memory. We can actually address it as memory. And for that, we need a couple of technical issues. I talked about the MMU. We need a way of doing flushes as well. I won't cover that. That's too much detail for this. But basically, it allows you to access this stuff as memory rather than as SSD or a block interface. So, application modification. Can we modify applications to take advantage of persistent memory rather than just treating it as disk? And the answer is yes. And there are lots of libraries out there to help support this. You may have come across some of these. There's one website I would point you at. It's called pmem.io. And pmem.io has a set of libraries, it's on the back-end slide, that allows you to treat this stuff and address it through libraries and already written APIs that do the right thing and work in multiprocessor environments. So we've got lots of language bindings for these libraries. You know, memlog, memobj, memblock. There's a variety of them to allow you to take advantage of this from your applications. And this will be the way we move forward with it, by the way. I doubt you will address persistent memory directly. The operating system might, but you probably won't. You'll probably do it through a library, through an API. So there's memkv. We were talking about memcached yesterday. There was a presentation about key value stores. This is the equivalent for persistent memory. By the way, you can use these right now. There's nothing stopping you using them right now. They're available, and they will work against standard memory or SSDs, because they actually have a back end that allows them to look like persistent memory. So a full stack example might consist of your application sitting on top of Cassandra, which sits on top of LLPL, which provides all the Java stuff and the allocations, which sits on top of what this persistent memory development kit, the PMDK that you'd get from PMEM, that provides you with the transactions, abstracts away the hardware, and at the bottom of this, there's this persistent memory file system that we've developed in SNIA, where we're exposing this thing as a set of memory map files, regardless of what the underlying technology is. It might be SSDs, it might be persistent memory, it might be just DRAM backed up by disk. So there's a variety of ways of actually taking advantage of this right now. You're future-proofing. In other words, if you write to these APIs, you're actually future-proofing your applications as we deliver PMEM. So, lots of ways to use it. Use the existing APIs. Try abstractions. It's great having load storable stuff that's persistent, but abstractions are much easier to handle. So key value abstractions are often easier to handle than actually addressing the memory yourself. Use a transaction library. There are transaction libraries out there as well. And if you must, go for raw mapped access, but that's going to actually take some effort and makes your application a little more dependent on what comes down the line. These libraries will allow you to mask out any technology changes that take place underneath them. So where are we heading? Lots of use cases, lots of high-level abstractions, lots of support, lots of language support in particular, and lots of excitement, because I can't tell you, it's really nice to have stuff. We used to think that having SSDs that went fast was really nice because you looked at a disk and it was incredibly slow. And SSDs were like, superb, we've just managed to increase our transaction rate tenfold by swapping out disks for SSDs. Well, imagine increasing your transaction rate 100-fold by swapping out SSDs for persistent memory. I mean, it's that scale of change, and it's incredibly exciting. So remote persistent memory is the last thing I want to talk about. It's all very well having this stuff tied to a server and inside a server, but like disks, you want lots of it. You want to be able to address it wherever it is. And we're doing remote persistent memory. That will be things like persistent memory over fiber channel, or persistent memory over TCP, or persistent memory over QUIC, or whatever transport protocol there might be. And that will actually slow the stuff down. You remember this? So if that's my persistent memory latency, obviously if my disks are a couple of miles away, that's going to actually add a bit of latency to it. But the idea is to try and get as much persistent memory as close to the servers so that we can build out large infrastructures and not have to build these monster one box, everything within 3 feet cubes that consume 10 kilowatts and take, huge amounts of power to cool. You can't treat it quite the same, but it's pretty close. You can treat persistent memory as like a NUMA model if you've ever come across NUMA. That's basically the ability to address this stuff as memory, but across a network. So, Java, there's going to be lots of support for Java. There already is in place. Again, pmem.io covers some of this stuff. There's a lot of investment by organizations like Intel in supporting language bindings. That's actually quite key for them. Cassandra, and there's a question at the back end, can persistent memory offer Cassandra opportunities for simpler code and improved performance? Well, I don't know about simpler code, but improved performance is definitely the case. I mean, quite literally 100 times better performance, 100 times better transaction throughput using persistent memory over SSDs. It's hugely significant, hugely. And there would be a Cassandra stack. And again, you'll see there that what we're doing is isolating Cassandra from the underlying infrastructure at the bottom, because these are pluggable interfaces. So there's a pluggable storage engine and a persistent memory storage engine that you can plug into Cassandra to actually get the benefit of using persistent memory. So there are some links to websites. Apologies for overrunning very slightly. I did this last year as well. I was so excited I couldn't get off stage. But the other thing I'd note from last year to this year is if anyone's interested in writing to this stuff, if you're developers, people like GridGain, for instance, we have hackathons where Intel are loaning out equipment, and they're sponsored by Google, where we're doing these persistent memory hackathons where people are coming along and developing for persistent memory. And they're generally free apart from the travel costs, hotel for an overnight stay. We're also going to be doing some over the internet. We're going to do a couple of online ones coming up this year. So you'll be able to try and, you'll get tuition and the ability to try this stuff out over the internet. And that's the website at the bottom, pmem.io. Any questions? I didn't answer the question how much, obviously.
What's the endurance compared to standard?
Endurance will change. Well, it depends on the vendor, but the endurance of these things will be considerable. We're talking 5+ years. So, endurance will not be an issue.
How many writes?
5 years worth. If this stuff is memory and it takes 200 nanoseconds to do a write, we'll do 5 years worth of 200 nanosecond writes to it. I mean, people are going to be delivering this with long endurances. Big endurances.
Same as SSDs?
Better than SSDs, actually, because flash technology uses a completely different mechanism. Persistent memory currently uses glass, and it melts and remelts small bits of glass, whereas flash actually moves electrons down holes. So it's a completely different technology.
I come from a university, and I run a research group, so my question is a little bit different. The question I have in mind is there any drive towards sort of processing, like you got the persistent memory, basically what you're doing is you're trying to replace the existing memory with persistent memory. And as a result, it's still a von Neumann architecture, right? For example, we're moving data from one point to another. So is there a drive for example, putting a processor inside of memory?
Okay, so there are two questions there, and I'll answer both of them. First of all, this is not a replacement for existing memory technologies. This bridges the gap between DRAM and its low nanosecond range and SSDs or flash and its microsecond range or mid microsecond range. We're trying to bridge the gap. This is, if you like, all programming is an exercise in caching, okay? And what PMEM gives us is this persistent memory layer to add to our ability to cache data. So it's going to be smaller, but faster. So it's not a replacement, it fits in the middle. The second question is, what about putting processors on the memory bus? And the answer to that is you should join SNIA's computational storage twig. There's a technical work group that does computational storage, where we're going to put compute on the persistent memory. There are various bus technologies being talked about. You may have heard of Gen Z or OpenCAPI or C6 to allow really, really high bandwidth access to these things in the terabyte range. You know, terabytes a second range. So there's a lot of work taking place. Computational storage is an interesting one because that's really one of the applications of persistent memory. Computational storage, I'll give you an example of computational storage. Imagine you're going out currently and building a system that can answer the question, how many red objects are there in this vast data lake I have? And what I have to go and do currently is go and ask a whole bunch of dumb devices to pass back all their data so that I, the CPU, can filter out all the red ones. And you know, that can take a huge amount of processing power to do. Computational storage is about sending the question out to the device and saying, do you have any red objects? And the device coming back and saying, no, none. And that's the message. It's really short. We're not having to transfer any data. So computational memory is exactly the same. It can answer questions about its own contents and provide you with different interfaces to that memory. So the computational storage twig is the place for you. So have I got enough time to take one more question?
So is that like an FPGA thing or a microcode thing? Or
What thing?
is the processor on the memory chip? Is that
Yeah.
like an FPGA kind of thing, or do you write a microcode?
Well, the computational storage, there are two types of computational storage fundamentally. The first is the pretty dumb computational storage that might be provided by, for instance, an FPGA that does things like compression and deduplication. Or security. Security is another issue with this stuff because you've got persistent memory, you've got real security problems. So security might be an issue. And then there's the smart devices with downloadable, effectively operating systems where I could run a mini Linux out there on the device itself and have the device be really, really, really smart. And those are quite different solutions to the same problem, which is we want to do the computation next to the data, not the computation having moved the data. Not moving the data is the trick. Okay, thank you. Thanks very much.